Right, recording, rolling, made to Friday, April 8th. Right, so some guys were trying out that Van de Graaff. So yeah, it's working so today. It has a kind of on off days, right? Yeah, maybe because of humidity, maybe because there's like a wire brush in there that has to touch the that latex belt just right. I'll leave it back there next week too. Okay? Let me switch my screen while you guys are looking at this electric field line. So one thing I was going to tell you guys yesterday was what you're looking at right here. So electric fields, because I told you about it's about electrostatic force. That'd be like something to do with the interaction between two particles. But well, there's what about just if you have a single charge particle? Well, there's an electric field associated with that. And there you go. You can see these electric field lines. Okay? See if you have opposite charge particles, those field lines will connect, so they'll track together. Also, there's a convention you draw from positive to negative. So there's like direction arrows, right? So it gets in that direction. Okay? Similar thing with magnetic field lines. There's a convention to draw from like north to south. Okay? And then, if you have the same charge particle, see how those field lines don't cross at all? Like that. All right. Let me switch back over here. Because I've got sort of a similar demo here. Once you guys see the animation first, because it's easier to see, but got a couple of bar magnets underneath these. Got a bunch of metal bars in here. You guys see this? Right, free to move around. Right now, these magnets, you're going to want to know where the poles are, because hand these to guys next week. Have you guys build some motors and some compasses with them. Right, the poles are on the faces. So there's one pole here. It might be the north pole, for example, and then you flip this thing over. Like this might be the south pole. Now I can know for sure if I either hang it from a string, it would align to Earth's magnetic field, or if I put it in a cup of water, like a water, put it in a cup that's in some water that could float around so it could turn. Okay? That would be a basic compass. You could do that too. Probably have you guys do that next week too. Okay, but just for this one, I know that's those poles are, this might be like north and south because they're pulling together. But if I flip this guy around, like north and north, now I can really feel them pushing against each other, right? As they were playing with magnets. So let's do this. Let's put like north and north, both facing up, or the same side facing up. Okay. So what happens to these field lines? Ooh, look at this. Yeah, I see how like these metal bars right here are like bending like this way and then this way. Just like that animation you saw. Okay? Animation is a little clearer, but you see the same thing here. And we take this one, flip it around. Okay. Now these, whoops, these always one pull together, so I have to pull them apart. Okay. Do you guys see these bars, these metal bars in the middle? See how they're like parallel? Those field lines are like pulling together. You guys see that? Okay. Now, of course, these are magnetic field lines, not exactly electric field lines, but it's analogous, right? It's like the same looking thing. Okay. And what's the math with that? Is that it? Wait, where's my page go? Well, okay. Here it is. So electric field, electric force, which we did yesterday, is KQQ over distance squared. So remember, this is analogous to gravitational force, right? Instead of two masses pulling together, okay, now it's two charged particles that could be attracting or repelling, right? So get two directions on that. There's still an inverse square relationship with distance, right? And instead of gravitational constant, now it's electrostatic constant, which is like 20 orders of magnitude bigger than gravity constant. Okay? But what if you knock out one of these charges? So you just have a single point charge. Well, now there's not a force, but there is a field, and that's what this top line is saying, right? So electric field, this could be newtons per coulomb, right? That's how you can measure it, newtons per coulomb, KQ over distance squared. Right. Remind you guys of something. So AP Live reviews are not quite open yet, but in 10 days on April 18th, I posted this to Google Classroom. If you go to, say, this link, youtube.com/advanced placement, you can see some live reviews for any of your classes. For physics, it's at 5 o'clock. So just remind you guys that it's just one more opportunity. But also, last few days, I've been reminding you guys that I've been opening up all those extra questions on AP Classroom, a lot of multiple choice per unit, like every single unit, there's lots of multiple choice. There's also a bunch of FRQs up there. There's also entire practice exams up there. Now, I don't have a formal homework for you guys for this weekend. So I do highly recommend that you write your planners for this weekend. Hey, take some time to study for this class. And those are all really good opportunities, right? You just open a Classroom, say, well, I want to do like these 2 or 3 sections and just answer a bunch of questions. Yeah.
When you turn them in, do they get the answers?
I think it should. Yeah, I think it should. Does it normally, like if you hit submit, does it normally tell you what they what you got right or wrong?
After the enclosures, right?
Oh,
After the exam.
Yeah, I think
Yeah,
it
it
takes
takes
a
a
couple days.
bit, but I think. Yeah.
okay. So it normally doesn't tell you the answers right after you submit it, but at like a few days later, like after the day closes.
I don't
Maybe.
think it does it for FRQs.
Okay, but okay, and then not for FRQ, right? Tell you what, try that. So answer some of those, wait a few days, and if it does not tell you the answers, then tell me, because I did put a due date of like May 13th, which is the day after your exam. So if you want me to, I can actually close them early. So if that helps, like give you the answers, let me know if you need me to do that. Okay. Okay. So next thing, let's do a quick glance at what you guys saw yesterday. We'll finish these notes. So you guys saw electrostatic force. Now, again, probably won't get any AP questions on this, but you actually there is one question you might get maybe on the AP exam, which has to do with the order of magnitude of the electrostatic force compared to gravitational force. If they ask anything at all, it might be something like that. Like you just have to know that gravity force is considered to be very weak compared to electrostatic force. Electrostatic force is like many orders of magnitude stronger, right? Even the constants like 20 zeros bigger. You guys saw for the first time yesterday the last variables and corresponding units that you'll see in this class. Right, so point charge you can measure in coulombs. If you have some flow rate of coulombs, that's called electric current. You can measure that in amps. 1 amp is 1 coulomb per second. Right. To go back, a lot of usually amp is considered one of the base SI units, so you can derive coulombs by doing amps times seconds. So this way, right? Right now, why would current flow? Well, because there's some potential difference called a voltage measured in volts. Right? For example, a battery, this one's like 9 volts, right? Would induce some potential difference. Right? And you also want there to be some resistance in a circuit, because if you don't have any resistance, saying yesterday, if you take just take a paper clip or a wire and touch both leads to each other, the paper clip gets really hot really fast because there's a lot of current flow, because there's almost zero resistance. And that will drain the battery really fast. One last variable down here is one that you already know from last semester, power measured in watts, right? Because this is a rate of energy, like joules per second. Right? That's what a watt is, right? But it also ties into some new formulas. Right? So there was Ohm's law says that current is caused by a voltage acting on some resistance. Right? So current is directly proportional to voltage. Double the voltage, double the current. Right? And also inversely proportional to resistance. Right? More resistance, less current. Right? A lot of times Ohm's law is rewritten like this, right? As a non-fraction. And then how does power enter this? Well, I give you guys 3 perspectives on power. So power is current times voltage, or if you sub in Ohm's law different ways, you can also get these perspectives on power. And these are good too. Sometimes, depending on what question's asked, sometimes you actually want one of these other perspectives because you can answer the question real fast. I gave you guys an example yesterday. Solve for a resistance in a bulb, be like so many ohms, given so many watts and so many volts. It should be right. I give you guys this analogy. Electricity flowing through wires, kind of like water flowing through a pipe. For me, I didn't understand this back in the day for a couple of weeks until I saw this analogy, and then finally everything clicked. So voltage, think of this kind of like pressure. Your battery is kind of like a pump trying to push electricity through. The current that results, think of like flow rate, like gallons per minute, or something like that. And the resistance, well, think of that kind of like a current in the pipe, right? So something like that. Like a classic example of a resistor might be like this here light bulb, right? It's providing some resistance. So this light bulb right here is kind of like this current in the pipe. Then ran some very basic calculations. So you guys saw a schematic. You see 2 parallel lines, one shorter than the other. That represents a voltage source like a battery, right? So many volts. Right? This jagged line symbol that refers to your resistor, for example, a light bulb. This could be a very simple circuit. So the direction of positive flow might be clockwise. The electrons themselves might be physically moving counterclockwise, but we'll trivia there, right? And so Ohm's law, you can calculate the current based on this voltage and this resistance. Boom. You can also go one more step, figure out what is the power output in watts, what's the rate of energy. Right? And then we started to get into a little fancier looking circuits, right? What if you have more than one resistor? Well, there's different ways you can wire them up. Very simply, you could put them sequentially, one after another. That's called in series. And then the total resistance, you just add them up, right? So R1 plus R2. So right? Then you can figure out what's the current, what is the power from there. Another way you could wire resistors is called in parallel, and that's if, this like rungs of a ladder. So imagine the electricity flowing around here. Whether you do it this way or this way, it's mathematical term. The current's going to split, right? It's going to split. One analogy for a current, I mean, I told you flow rate, like gallons per minute, like the gallons per minute, right? Could split. Could be like traffic flow, right? Some number of cars, like if you have a stream of traffic, like 100 cars, well, that traffic's going to split, right? Most of the cars are probably going to take this 3 stoplight path compared to the 6 stoplight path, but it's going to be advantageous for some proportion of traffic to go this way too. I'm hinting at Kirchhoff's rules, which I'm probably going to have to save for Monday, but we're going to dig into a circuit and figure out exactly how does the current split, this electricity flow around the circuit, right? So the total resistance, you can do 1 over the total resistances, and you can write a bunch of fractions, 1 over R1 plus 1 over R2. If I had like 5 resistors all chained like rungs of a ladder in parallel, you do plus 1 over R3 plus 1 over R4 plus 1 over R5, right? You just keep chaining them like that. Now, if you only have 2 resistors, then you could actually cut through some math here, say common denominator, blah, blah, blah. It ends up being product over sum, but this only works for 2 resistors, right? We'll do a bunch of calculations next week, and then this will all come back, do some examples here. All right, so that recap from yesterday. Now what we do is we're going to switch over and play a bunch of Paul Hewitt demos. Paul Hewitt. So switch my computer over. Right.